For the past several years, we've been developing devices to conduct all kinds of mosquito control missions like liquid larviciding, dropping tablets, collecting larvae, or making granular applications with UAS. But our biggest challenge has been making ultra-low volume applications of pesticides for adult mosquito control. We tried this back in 2015 with limited success. I actually modified a Micronair miniature rotary atomizer for ULV applications. It worked, but had some drawbacks. The flow rate was not high enough, the droplets were too large. Because the droplets were just flung off the atomizer, much of the pesticide got caught in the prop wash and was recirculated onto the frame of the aircraft, and it was somewhat hard to make, so I started over. Eventually, I found this, the Longray Eco UOB, also sold by Adapco as the Pioneer. It's a handheld, battery-powered ULV sprayer. It runs on 28 volts, which happens to be the same voltage as our UAS. It has an electric blower that generates 40 miles per hour at the nozzle. There is an adjustable flow rate from 1.4 to 11 ounces per minute, and it weighs in at 13.4 pounds. And this looked like something that I could adapt to our UAS. The first thing I had to do was trim the fat. In stock form, it's too big and too heavy, so I opened one up to see what parts we really needed. And here are the important parts. And this looked like something I could work with. So I repackaged those parts into a compact ULV sprayer for the UAS. Everything in green was 3D printed in ABS plastic. You have the electronic control board here, and the flow control here. This is a quick release dovetail mount that just slides in place. And there are only two wires to connect, one for the battery and one for the control system, so the whole unit can be mounted or removed in just seconds. I swapped out the original tank for a lightweight 20-ounce tank, and the final weight is only 3.9 pounds. That's a 71% weight reduction over the stock unit. With the unit complete, I ran some lab tests with a DC-4 Droplet Counter. The flow rates ranged from 1.4 to 11 ounces per minute, so you have a nice wide range. Median droplet size was 23 to 58 microns, depending on the flow rate. Now there are high and low fan settings, which should impact the flow rates and droplet sizes, but there was no difference between these settings. The flow rates, airspeed, and current draw on the battery were exactly the same, regardless of that setting on the machine. So the high and low settings had no effect. And this was true for all of the units that I had, not just the one that I modified. So I don't know if there was something wrong with the units I received, or if they're all like this, but it's just something to keep in mind. The UAS system that we used for this sprayer was the DJI S1000 Plus octocopter frame with a Pixhawk flight control system. It's 41 inches in diameter, not including the props, weighs 16 pounds, can carry up to 24 pounds and fly for 32 minutes and reach speeds of up to 45 miles an hour. It's a very well-built frame with a folding design that makes it easy to transport. It's capable of running fully autonomous missions by programming those missions on this tablet, and of course there's a remote control for manual flight. Now in 2015, when we tested the original sprayer, we set up a 3x3 grid with rotating impingers. Then we flew low and slow upwind of the plot, mimicking a truck-mounted application, relying on the wind to carry the drops across the plot. We ended up collecting some droplets on this first row, but there was almost nothing on the other rows. What we found was that most of the spray was getting caught in the prop wash and forced straight down onto the grass. So obviously we needed to try a different approach. To test this new unit, we set up another 3x3 plot with 50 feet between all the cages. But rather than flying upwind, we flew a pattern directly over the cages with 20 feet between each pass, 20 feet high at 7.5 miles per hour. And this is what the pattern looked like. Now this was a completely autonomous flight, everything from takeoff to landing. We applied BVA oil with UV dye at a rate of 50 milliliters a minute using FLB spinners and Teflon rods to collect the drops. And here's a video of one of the applications. You can see the UAS is very stable, maintaining a constant speed and consistent altitude. It rotates at the end of each pass so that the spray is always coming out the rear of the aircraft. And here's a view from on board the UAS. You can see it flying directly over the spinners, and then turning around for the next pass. And if you look closely, you just might be able to make out the spray coming out of the nozzle. After the field trials, we ran the Teflon rods through a fluorescent microscope with drop vision software, and here are the results. The droplet sizes are on the x-axis and the droplet count is on the y. We have a nice narrow spectrum with a VMD of 16 microns and almost 3 drops per square millimeter. And based on my experience, results like this should yield excellent mortality in caged bioassays. So what can we do with this setup? These graphs on the right compare the current draw on the batteries under normal flight conditions without the sprayer to the current draw with the sprayer attached and powered on. The average current draw is given here. You can see we're using almost twice as much current, which means our flight time is cut in half. So we end up with about 16 minutes of ULV flight time. In this test, we sprayed 0.43 acres in 1 minute and 35 seconds. Assuming a 20-foot swath, that gives us a minimum of 4.5 acres sprayed per battery. The further we can stretch out that swath, the more area we can treat. But even at 4.5 acres, that's a pretty reasonable treatment area for a UAS. So what's next? You might be wondering why we didn't spray caged mosquitoes. It's because applying pesticides with a UAS requires special permission from the FAA. Currently, we're in the process of becoming public aircraft operators with the FAA. That will enable us to make pesticide applications, and then we can run our cage trials. We flew at an altitude of 20 feet with 20 feet between passes, but that was arbitrary. We need more trials to establish the actual swath width at different altitudes. And while this sprayer design is pretty good, I think there's room for improvement. I'm going to talk to Longray about possibly creating a new ULV sprayer specifically designed for UAS that is lighter and more power efficient. If you'd like to follow along with this project, we can be found under Mosquito Drones on social media, or you can contact me directly at this email. Thank you.